my name is John. I am as you said, a PhD at a group named CRAI, or Computational Radiology and Artificial Intelligence at Oslo University Hospital. And today I will talk about deep learning-based MRI reconstruction. So why do we need to accelerate MRI? Well, MRI can be slow. It can be uncomfortable, said by someone that's spent a couple hours too much in the scanner, and you want to increase the total patient throughput and just make the patient more comfortable. So for these reasons, well, accelerated MRI is critical in the clinical workflow. And besides being uncomfortable or whatever, if the patient moves during the scanner, it can introduce so-called imaging artifacts. And the most common one is a motion artifact. And that happens when mid-scan, the patient might move their head or something like that. You go from what's a decent or good-looking MR image, for example, the one on the left, to something that's a bit more noisy, a bit more difficult to see. And for that reason, it's quite important to make sure the scanning goes fast to avoid these kind of problems. And you can also have cases where it's difficult to make the patient go through a full scan. For example, they can be in pain or similar things like that. So the acceleration of MRI is quite important. And today we'll talk about first the MRI signal, so I can give everyone a general basis of what we need to know. So we'll talk about the actual sampled signal during the scanner, how we manipulate it, what kind of transformations we do, and similar things. Then we will go over to the reconstruction model, how we actually want to reconstruct the data, how we can go from a downsample scan, how we can use deep learning to accelerate the MRI. And finally, we'll talk about some experiments that I've done and the results. How does the reconstructed images look? So first, the MRI signal, also known as K-space, I will probably switch a bit between the two, but they are the same thing. It's a complex signal, meaning it has a real and imaginary component, and the signal comes from N receivers or receiver coils. So when you go into a scanner, you often get like a head coil, just a large receivers that has multiple minor receivers scattered all around your head, and each of them sample the signal. So you get tons of signal. And they are connected to the image, the actual MR image, the one that the doctor or the radiologist wants to look at, through the inverse Fourier transform. So every single coil gets its corresponding real and imaginary image. And these doesn't look particularly good. So those are not the images you use. And to go from the coil images, so coil 1 has the real and imaginary image, coil 2 has its corresponding real and imaginary image, you first square every single coil image, and then you sum them up, and then you take the square root of the image. And what you're left with is a pretty nice looking image. Then the question is, how do you accelerate the acquisition of signal, or how do you accelerate an MRI? First, we'll just ignore all hardware-related acceleration methods far beyond this topic. But the way you do it, if you don't use any hardware-specific acceleration method, is that you downsample the signal. You sample less signal. So if you sample half of K-space or half of the signal, you accelerate the scan by twofold, or it goes twice as fast. So example, you can do it by removing lines like this. In this case, you have, I think it's 1/8 of the total signal. And the scan will therefore be 8 times accelerated, or it will go 8 times as fast. The problem is that it also introduces some aliasing artifacts. the image is no longer of clinical quality and it's quite useless. So it doesn't really matter if you're able to accelerate the image if you can't make the image look decent. And there's also different methods of downsampling. You can also do this, where instead of downsampling line-wise, you can do it like point-wise like this. And the reason you do it differently is just dependent on the scanner. So some scanners allow for this kind of downsampling. It's generally better, and it's what's used most commonly, but it depends on the scanner and also what kind of scan or what kind of sequence the radiologist wants. And you can also see that the pattern of downsampling highly affects the image. So the last one was more blurry and was more stretched almost and looked like it was duplicated on the sides, whereas this one is more noisy. So it affects how the image looks. So how do you go from the downsampled image to a image of clinical quality with deep learning? Well, the initial approach, and one of the first one, this was far earlier than when I started with this, was to quite simply give a model, a unit, for example. Unit works great in medical imaging. Just give it the downsampled version. So you can give it this one or this one, the image on the left. And then you have the model chew through the data, chew through the image, and the goal is then for the model to output the image of how it would look if it was fully sampled. So you want them to train the model such that it gives an image of how it would look like if you didn't downsample it. And how you do that is quite simple. You just have the fully sampled one, and then you have the retrospectively downsampled one. So you downsample by applying a mask just before you input it into the model, and then you just want to minimize the absolute distance or the mean square error between the two. So that's the initial or the first approach, and it works quite decently, but it's not the best, which is why another method was created, or another type of model was created, which was called the Cascaded reconstruction network. And the way this works is that you give it the downsampled signal, not the image itself, but the signal. So we give it the case space where multiple lines or multiple data points are removed. And then you feed it into a network, similar as previously, a unit or whatever you want to give it, and it alternates between a subnetwork, so the unit, and then to data consistency, and then back to the subnetwork data consistency, and back and forth maybe like 10 times, maybe 20. Of course, you have to stop because you need to think about the reconstruction time itself, and then you output the image, the reconstruction. That's the general flow of how this kind of method works. And it's illustrated here. So we give it the downsampled data. And the first part of the network is something called coil sensitivity estimation, right here. And the goal of this is to estimate the sensitivity of the receiver coils. So you want to figure out where each signal receiver is the most sensitive. So if you have a receiver on your right side, it will have the most signal from that region. And you want to do this for every single coil around your head. And then the second part of the network is the iterative part. So you iterate between a convolutional neural network, a unit, we like units in medical imaging, and you do the data consistency. And you can see there's something called coil reduction and coil expansion in there. And those operations uses the coil sensitivities to first reduce the dimensionality of the data. Remember, the data is, you have n receiver coils, and it can be 30 receiver coils. So you have 30 complex images, both the real and imaginary components. So it takes a lot of space and it uses a lot of time if you want to process all of it. And you have something called coil expansion, where you expand the dimensionality. You get back to the actual dimensionality of the data. So first, the coil sensitivity estimation. The model estimates the coil sensitivities for the real and imaginary components for every single input coil. So for every coil on the scanner, it gives the sensitivity estimations there. And as I said, they're used for first dimensionality reduction, where you simply just multiply them with every single coil image, and then you sum them up together, and you end up with a single complex coil image. You end up with the real and imaginary component of the sum of all the coils. So we go from, say, 30 coils down to 1. That's both a lot faster if you want to process the data, but also a lot less memory intensive during training. And the second thing is the dimensionality expansion. This is quite simply the opposite operation. You multiply the single reduced coil image with the coil sensitivities to go back to the coil images. So you want to go back to the images the scanner scanned. And then we have the data consistency and the convolutional neural network part. So let's imagine you have a MR signal, the bottom left, known as K-space. And then you input the single coil image, so the complex image, into a model. And then it goes through the models, and then it outputs the corresponding complex coil image. That's the initial approach. That's the first approach that was done. So how does this differ? Well, from that complex image, you multiply it with the coil sensitivities. So you go from the single complex output of the CNN to the output or the prediction as how it would look like for every single coil. So you expand the dimensionality. And from this, you can go back to the actual MR signal by using the Fourier transform. So you go from image space to frequency space. And here's the data, here is where the data consistency comes into play. You already know part of the signal. Like when you have the patient in the scanner, you sample, say, 25% of the full MR signal. You already have a part of the ground truth. You already know how 25% of the data is going to look like. So the data consistency is quite simple. You just copy paste it over onto the predicted data. And then you have a prediction of 75% of the data, and you have the ground truth of 25% of the data. The exact way these are copy pasted is determined based on the method. I just use the weighted sum. It's what works best in my experience. So if you summarize, you start with the downsampled MR signal. So how it would look like if you had a patient in the scanner and you said, okay, we want to do a scan that's 4 times accelerated. You first estimate the coil sensitivities. Then you reduce the dimensionality of every single coil image to make sure it's easier to just predict. You reduce it so you don't have as much memory overhead. And then from there, you refine it through the first CNN. You do the coil expansion and you do the data consistency. You already know a part of the ground truth, so you enforce this form of prior knowledge into the model. And then you can continue with this form of refinement over and over and over in an iterative type of process. So commonly use like 12 iterations, 20 iterations to do this. And the final output is the absolute, or is the magnitude image. It's the reconstructed image of how you want it to look. So that is the general flow of how a MR reconstruction model works. This is how it is used and how it's implemented. But when I started, I thought, well, it's, as you can see, it's really long. If you have 12 units stacked after each other, it will, first of all, use a lot of memory. But how does the gradients flow throughout the network? It has to degrade somewhat. So what we did was that, okay, we used a baseline, a reference model, and we added residual connections into each unit. We added dense connections, these ones. So from each subnetwork, from each CNN, we added a set of dense connections to the next one and to the next one and so forth. And lastly, we added something with the interconnections. It's really just dense connections, but within the network, since we thought that a lot of the information that the model, or a lot of the information the model gains and some of the information in the feature map might get lost. So you want to try to preserve them across subnetwork, across cascades. And we tested these 3 modifications on 4 times and 8 times acceleration. So we tested them with 25% and 12% of the total data. And to do this, we used the FAST MRI dataset. The FAST MRI dataset is luckily a publicly available dataset from a group in New York, and they have scanned 4,469 patients with different kind of pathology, with different kinds of sequences. So they have a sequence called T1, called T2, and called FLAIR. And just think of the different kinds of sequences as just different forms of image contrast or different flares of the same image. They look quite different. For example, in the bottom right here, it is a T1 weighted image. Yeah, and the way we train the model, or the way we use the data, is that since the data is fully sampled, we can simulate how we want to, or how the scanner would downsample the data, or how the data could be downsampled. So first, we start with the case-based data. We use the inverse Fourier transform. It's just to crop out empty regions, because the images are quite large. They can be like 700 times 300 in height and width. So it will use a lot of memory. So you have to try to reduce it where you can. And then you can Fourier transform it back to case-based. And from there, you simply multiply it with a downsampling mask of your choice. So you can multiply it with a 4 times or 8 times acceleration mask, and you will get the downsampled image. But you'll also, since you already have the fully sampled data, you can also get the MR image you want to reconstruct. So you have the ground truth, but you also have how the downsampled image would look like if you did it on a scanner. So first, the proposed modifications, so the residual connections, the dense connections, and the interconnections, so the dense connections within the network, improves the SSM, which is a metric for how good the reconstruction is, with the maximum being 1, by 8 and 11% for 4 times and 8 times reconstruction. So it's quite a significant improvement. But you also have to have in mind that the reference model we used, with the baseline reconstruction methods, are quite good to begin with. So it might sound like a lot, but visually it's not that different, because the networks are already really good. But for every type of sequence that they had, there was a improvement, as you can see in the violin plots, where the leftmost violin plot is for the reference model, and the right counterpart is the proposed model. We dubbed it the densely interconnected residual cascading network, in the lack of a better name. And yeah, it just generally did better for all type of sequences and for both acceleration factors. And we were also curious to see if the proposed or the implemented alterations in the network actually improve the gradient flow. Did it actually make the gradients propagate better? So we trained a model where we calculated the mean gradient for every single subnetwork. So if you have 12 CNNs, we calculated the mean gradient for the first, second, third, fourth, all the way to the last one for both the reference model and the proposed model with alterations. And as you can see on the rightmost figure, the gradients are a lot more stable and a lot higher in general, and they don't degrade the deeper into the network you go, in contrast to the reference model, which is the red one. You can see that the first cascade had almost no gradients remaining in contrast to the first one, or the last one. So let's take a look at some images. On the top row, you can see the ground truth image. So this is the fully sampled image. And the middle row is the fourfold accelerated one. So 25% of the data, or 4 times accelerated. And the bottom line is the 8 times accelerated. And in general, the reconstruction are quite good. They perform well. But they struggle when the acceleration factor gets too high. And they can have a tendency to imagine pathology. So they can imagine imagine not a tumor, but more like just some liquid or something like that. They can imagine some pathology, but that's only prominent for eightfold and higher. And it also have a tendency to act as a smoothing filter. If you go real close to the screen, you can see that the fourfold and eightfold are a lot smoother than the ground truth. And here's another example where we plotted the single image, the ground truth, with the reference and the proposed model for fourfold and eightfold acceleration. And if you look at the middle row, you can see the absolute distance between the ground truth and the proposed models. And in general, the proposed one had better reconstructions and had a smaller error. And you can actually see it on the bottom right one, where the proposed one is slightly closer to the pathology. It should, of course, be mentioned that this is quite difficult to see if you try to look for it, because the reference model are really good in general. Yeah. So although the models work great, although the deep learning-based reconstruction methods work great, they're still not perfect, especially for the higher acceleration factors. So here's an example of the ground truth to the left, the 4 times accelerated in the middle, and the eightfold to the right. As you can see, the area of interest is getting smoother and smoother, or more smudged for each factor of higher acceleration, and it generally is less and less similar to what the ground truth image is. And this is especially noticeable for the rightmost image. But other than that, the image looks pretty decent. And here's another example that's a lot easier to see. You have a white hyperintensities on the left one, the ground truth, and you can see it on the middle one, the fourfold acceleration one, so the 4 times acceleration. But the hyperintensity is completely smudged or removed on the rightmost image. So it has a tendency, as I said, to remove or imagine pathology. And in this case, it didn't have enough signal to be able to reproduce the pathology. And lastly, I want to show a bit of how it works on prospective data. So if you try to use the model on data from the scanner, so if you have the raw data, an accelerated scan on the scanner, how does it look like in comparison to the scanner versions of the same scan? So on the left side, you have the scanner image. So this is an image during a intraoperative operation where you try to extract a glioblastoma. So mid-surgery, the patient is brought into the MRI, and you do a scan to make sure that the patient to make sure that all the tumor tissue has been removed. And of course, that has to go fast. If you have the patient lie there for too long or something like that, you might end up getting an infection or other problems. So these images are by default quite bad. As you can see on the leftmost one, it's quite blurry, but it does the job. And on the right side, you have the corresponding deep learning reconstructed image, and it's generally a lot more clear. It's a lot sharper than the scanner counterpart. And it's the similar here. This is a different kind of sequence. It's a flare sequence. You can see that the deep learning reconstruction has a smoothing effect and a noise removal effect, and has a higher signal to noise ratio in comparison to the downsampled scanner image. So what's left for this? Well, deep learning based reconstruction, it shows great promise. The images looks great, but it hasn't been really done for clinical testing yet. So the next step is, of course, to do clinical testing. And another thing is that most reconstruction framework using deep learning, they only do the most common sequences. So the most common structural sequences, like the ones you've seen, like the T1, T2, and flare, most of which have been shown here. But they don't do more or less common sequences. So another thing would be to extend the use beyond structural MRI. For example, you could do something called elastography, where you try to estimate the stiffness of the brain. But that's a lot less common, so having fully sampled data is also a lot less common. And lastly, the models have a tendency to be very memory intensive since they're very large. They span multiple subnetworks where each one is its own unit, and all of them are 2D, so they can't reconstruct the entire brain. So we have to go a single image at a time. Yeah. So that's about it. Are there any questions?